So this function derivative is similar to itself. Yeah. All right. D.4. Now let's look at one simple example. Yeah. D.4. Yeah. But for this part, I do not talk about that choice theorem. So later we will do that. Yeah. Yeah. Our example, the input is exponential function. Yeah. So let's solve this relatively simple ODE. Yeah. So R function, like that. Yeah. So the first step, so you may feel a little hard to understand. First step, because we need to represent the structure first, the right structure first. Yeah. All right. Yeah. Because the main step, we need to find a YP function solution. Yeah. YH, yeah, very easy. Now, YH, we apply the formula. Yeah. All right. So the YP part, the question why you assume YP has this structure. Yeah. So that's the first question to answer. Yeah. Here you can see you represent it. Yeah. Actually, if you look at the original equation, there is some special property. Yeah. Because, so what's the special property? If you look at the characteristic equation for the homogeneous version, yeah, lambda squared plus 3 lambda plus 2.25 equals 0, then it has a double real root. So that is lambda plus 1.5 squared equals 0. Right? So it has a double root at negative 1.5. Now, then there is an interesting property here. At the right-hand side, the R function. Yeah. The R function, right-hand side, you can see the E function, the exponent part happens to be the same, matching that root, lambda, negative 1.5. Yeah. So with this special structure, how to choose the appropriate form of the YP function? We need to apply that choice theorem. Okay? Yeah. So I mentioned. Yeah, but at this point, I haven't shown you that choice theorem. Yeah. Yeah. So one of the 3 rules in that choice theorem, yeah, on our textbook. Yeah. Later I will show you that one. So we will closely study that choice theorem. Okay? All right. Yeah. So the structure, you need to apply the choice theorem. All right? Yeah. Then the C, that's the undetermined coefficient. You need to determine that C. Yeah. Because after you represent the right structure for the solution, if you plug in, yeah, you take derivatives, first derivative, second derivative, you plug in, yeah. So you will be able to find that C constant. You can solve a reasonable equation to find that undetermined constant C. Yeah. If your structure is wrong, so then you get some contradictory equations. Yeah. you cannot get the right solution. Yeah. All right. Here, let's plug in. Yeah. Y prime. Yeah. So you need to calculate the derivative. Yeah. Double prime. Yeah. Derivative. Yeah. Because all the terms, they have the same common factor, right? The e function part, e to the negative 1.5x, that is a common factor. You can cancel out. Yeah. After cancellation, yeah, so you have a algebraic equation. Yeah. But this equation, because your structure, yeah, based on that choice theorem, the structure is right, so you can find a C satisfy this equation. Yeah. If the structure is wrong, then you cannot get a reasonable solution. Yeah. By comparing the coefficients, yeah, let's comparing the coefficients, some cancellation thing, that C equals -5. Yeah. So here, the most important part is you need to get the right structure. Yeah. All right? So based on that choice theorem. Yeah. Later we will study. Yeah. Yeah. In part D, we delay it. Yeah. But we need to be aware of, so there is some important theorem behind it. Yeah. So in this way, we find YP function. Yeah. Yeah. Then the whole solution, the general solution, the lambda thing, yeah. So, and double root, we know C1, C2, right? C1, C2, but C2 we need to multiply X to C2. Yeah. So that's the YH part. YH part, you have this, E. Yeah. Yeah. And YP part, yeah, you have that. Yeah, but how do you determine X squared? So then, the choice rule, yeah, because based on the, yeah. So here, let me describe that choice rule, a theorem a little bit. Yeah. Why you choose X squared, right? Yeah. So give you the, some simple idea here. All right. First factor we consider. All right. Lambda has this root negative 1.5 that equals the E function here. Yeah. Happens to be the same. Okay. So that's the first factor to be considered. Yeah. If you have that condition, your structure should be that same E function times certain power of X. X to certain number, certain power. Which number? What number? That number is determined by the multiplicity of this root. Multiplicity. So what's the multiplicity? Yeah. So here the multiplicity here is 2. Multiplicity. Double root. Double root. Yeah. If it's a single root, then so your power function is different. But here it's a double root. Okay? Double root. Yeah. So, yeah. So based on these two factors, yeah, yeah, same E function, yeah. Second, same E function, then you need to look at the multiplicity of your root. Yeah. So that you can determine the structure in this way. Yeah. So that's the choice theorem. Yeah. All right. Yeah. Yeah. Otherwise, how do you know the structure, right? Yeah. Okay. So now we get a perfect solution in this way. Yeah. All right. Then we can apply the initial conditions to find C1, C2. Yeah. So you get your final solution. Yeah. So that's in this way, that's how we find YP function, YP solution. Yeah. All right. Yeah. D.5. Yeah. Now, this time we need to study this resonance problem. Yeah. Yeah. All right. Let's look at one application question problem. Undamped forced oscillation with resonance. Yeah. Yeah. All right. Undamped, yeah, remember that Y prime term is 0. No Y prime term. That's the undamped system. But you need to use a forced oscillation. Yeah? Forced oscillation, you have external force. Yeah. Forcing function is periodic function. Yeah, because forcing function has certain oscillation property. Yeah. So that system, you may have this resonance problem. Okay? All right. Let's look at the question first. Yeah. 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 All right. Yeah, here I just use a, similar system. Yeah, may not be perfect. Yeah, I just, find the motion of mass spring system with mass given, damping 0, so 0. Yeah. It means the C constant equals 0. Yeah. So this is the damping part. Okay, the damping part. So C constant equals 0. Okay. Yeah. So that term is gone. The spring constant K given. Yeah. Driving force, it's a periodic function. Cosine t plus minus 4 sine t, 2 pi periodic, right? So there is a period. And there is a frequency. Yeah. Frequency. Yeah. So actually, because when we study yeah. Yeah. What's that? What's this one? Yeah. All right. Initial displacement. Yeah. And velocity. So initial displacement 0 and initial velocity also 0. Yeah. All right. Therefore, what frequency of the driving? What frequency? Because here, if this is the driving force, because this driving force, yeah, we should add omega t, right? Yeah. Because this omega parameter can determine the frequency of the driving force, right? Yeah. Frequency of the driving force. Yeah. All right. Yeah. 2 pi over, omega over 2 pi, right? Yeah. Frequency. Yeah. Yeah. So we want to find for what frequency of the driving force would you get a resonance problem. Okay? Yeah. So we want to study that. Yeah. Yeah. So there should be some omega, appropriate omega there. Yeah. All right. Yeah. So let's consider. Yeah. So here, yeah. So here, yeah, first, yeah, because later we will switch to the omega version. Yeah. First, so let's look at this system. All right. Yeah. So initial condition. Yeah. All right. So that's the given information. Then to solve it, yeah, so let's try to solve it first. Yeah. Solve it, then you have, these two parts. Yeah. YP, right? Yeah. So you need to determine YP and then YH. Yeah. So YP should take this structure. Yeah. So cosine. So why YP take this structure? Yeah. So, similar functions. Yeah. Derivative. Yeah. Because the derivative, second derivative, yeah. Original function has the form. Derivatives have the similar form. Second derivative also have that form. Yeah. But this also part of that choice theorem. Okay? Yeah. But this part very easy. Yeah. Very easy. Yeah. All right. So A and B to be determined. A constant. So using our previous undetermined constant. So we need to determine A constant and a B constant that satisfy this equation. Yeah. All right. Yeah. So now, yeah. So this time I add omega. Okay. Yeah. So on this version, because we need to determine that omega. All right. Yeah. Yeah. All right. Solution. Yeah. This time we consider that omega to be determined. All right? Yeah. All right. Yeah. So there, YP in this form. Yeah. First derivative, yeah, because the structure compatible. Yeah. Structure compatible. So when we take first derivative, second derivative, then we replace the expression. Yeah. Then we have confidence we can find the solutions. All right. So second derivative. But first derivative, in our original equation, we do not use first derivative. So we only use the second derivative. All right. Then plug in. Yeah. All right. Yeah. Original equation here. Yeah. But after some simplification. All right. Yeah. Little a, little b to be determined. All right? Little a, little b to be determined. All right. All right. Then, how to solve this equation? So that's the question. Here you treat omega as a constant. Yeah. Omega as constant. Okay? All right. Yeah. All right. So how to find little a, little b from this equation? Yeah. So the way is you compare the corresponding terms. Left-hand side, you have cosine terms, right? Cosine function term. Left-hand side, you also have sine function term. You also have sine function term. Okay? Yeah. Simple way. The coefficient of the cosine function at the left-hand side should be the same as the coefficient of the cosine function at the right-hand side. The coefficient of the sine function at the left-hand side should be the same as the coefficient of the sine function on the right-hand side. So we have two equations. Yeah. Solving those two equations, yeah, A equals B equals this expression. Okay? Yeah. After simplification. Yeah. Right? 1. Yeah. Right? Yeah. So, yeah. Yeah, because you scale it, right? Yeah. So division you scale, multiply by 8. So, coefficient becomes 1, multiply by 8, it becomes 9. Okay? Yeah. All right. First, here, I try to answer your question. Do you have a question why we make why, in order to make this equation, always true, why we make this coefficient equals that coefficient. Okay, why make that part equals this whole thing. Do you have a question on that? Yeah? What we said? Yeah. So the answer is very simple. Yeah. Let me tell you the answer. The answer is these two functions, cosine function, sine function, they are linearly independent. We did that before, right? Cosine function and the sine function, linearly independent. They have this property. Okay? When these two functions are linearly independent, then you just compare two corresponding coefficients. The corresponding coefficients must be the same. That is, this condition comes from the definition of linearly independence. Remember K1, K2, okay? Yeah. Think about, we move this cosine function from right-hand side to left-hand side. You do subtraction, right? We move the sine function from right-hand side to left-hand. You do subtraction. You have K1, K2, right? K1. Yeah. So if you do that move, you get a structure, some K1 cosine omega t plus K2 cosine sine omega t equals 0, right? Yeah. But you know these two functions are linearly independent. Linearly independent would force K1, K2 must be both 0. Yeah, that's the definition of linearly independent. Yeah, so linearly independent, we know that fact by calculating Wronskian, right? Calculating Wronskian, sine, cosine. It's non-zero, so we know these two functions are linearly independent. Yeah, so the K1, K2, both must be 0. Yeah. So based on that, we can get the two equations. Yeah. Yeah. So solving those two equations, A equals the undetermined coefficient, the first one, little a equals this expression. B equals that expression. Based on the form of A and B, what conclusion do you have? When you look at the form of A constant and a B constant, do you have any conclusion? Anything special you can talk about? Yeah. Look at the denominator. Omega squared minus 9. Omega squared minus 9. What would happen when omega equals 3? What would happen when omega equals 3?
0.
Yeah. When denominator is 0, what's the value of A and B? Infinity. You know, if you interpret in your original application problem, the system exploded, right? Yeah, because suddenly that's the resonance, okay? The phenomenon. That corresponds to the resonance. So that means there is some special point. You cannot touch it. Even omega very close to it, may not be exactly close to 3. Okay, very close to 3. 2.999. Okay, very close. The value of A is huge, right? You know, value of A and B both growing super big, that means this solution, this YP solution, cannot be controlled, right? The YP solution, cannot be controlled. Okay? Yeah. Yeah. So you get that resonance problem. Okay? Yeah. The damage, you break the bridge, for example. The bridge has its own frequency, right? Yeah. Bridge has the natural frequency. Yeah. Here, what's the natural? Let's talk about natural frequency. Because natural frequency comes from the system part. Okay? So this is the system part. Left-hand side is the system part. The right-hand side is the external force part. Okay? Yeah. So the natural system comes from the natural frequency comes from the system part. Yeah. All right. So this system part, 0.125 lambda squared. Yeah. Let's look at the, let's look at the characteristic equation plus 1.125. Yeah. This is the characteristic equation, right? Yeah. All right. Then let's simplify it, multiply by 8. Yeah. So lambda squared plus 9 equals 0, right? Yeah. 9 equals 0. There, your lambda 1 equals 3i, lambda 2 equals negative 3i, right? Okay? Yeah. All right? Yeah? Yeah. So your general solution, look at your general solution, of the homogeneous part, YH, right? So YH general solution. C1 cosine of 3t plus C2 sine of 3t, right? Yeah. So this is omega 0, right? Omega 0 equals 3. Okay? From your system, this omega 0, corresponds to the natural frequency. Yeah. So although the definition of a natural frequency should be omega 0 over 2 pi, right? Yeah. Omega 0 over 2 pi. Yeah. Yeah. Now you can see the resonance occurs where your real omega, driving force omega frequency, driving force has a frequency, omega frequency, whatever, equals the natural omega, omega naught, okay? Where omega equals the omega naught, then you have that resonance problem. Same frequency, right? The frequency very close. Yeah, actually, if the frequency very close, it could cause the damage. Yeah. So that's some story. Yeah. I don't know if it's true or not. People across a bridge, because bridge has a natural frequency, right? Natural frequency. But when people walk, an army, walk, but they, use the same pace, okay? Yeah. There is a frequency, right? Yeah. If that frequency is the same as the bridge frequency, then the bridge breaks. Yeah, because the resonance. Yeah. So I heard, so when army, go through bridge, so do not use the same pace, okay? Just, use this random type walk. Yeah, yeah, just no frequency. In that case, no frequency. Okay, yeah. Otherwise, yeah, some story like that. Yeah. Yeah. I don't know if it's true or not. Yeah, but definitely, after we study this phenomenon, yeah. So when you design real world system, you need to be aware of it. This kind of problem. Yeah. 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 So from very simple linear system, ODE. Yeah. So, we can understand, this phenomenon. Yeah. All right. Yeah. Last about 10 minutes. Last time there is one linear independent concept I didn't explain clearly, so I want to use the last 10 minutes to talk about. There is a theorem in our textbook, so let's look at that theorem to understand the condition for the linear independence better. Yeah. But I need to switch to this laptop, so I need to stop sharing of this one and stop share. Yeah. In our textbook. Yeah. So let me explain the the bottom condition part. Yeah. First, ODE1. Let me write ODE1. Yeah. One we saw. Yeah. So that's yeah. Sorry. Let me. Yeah. All right. Yeah. Let me write here. Yeah. I need to write right here. Yeah. Change the pen color. All right. So ODE1, that is the y double prime plus p function y prime plus q function y equals 0. Okay? Yeah. Yeah, because this case, we only consider the general solution part. Yeah. Then the condition, these two functions continuous on open interval I, then two solutions linearly independent if and only Lorentzian. Yeah, all right. This is 0 at some point in I. Some point, only one point is enough. Okay? Yeah. So the result of this one, yeah, you calculate the Lorentzian of these two solutions, y1, y2 solution. But if that solution, if you can find one point inside that interval to make that W equal to 0, then you can say linearly dependent, right? Yeah. You already have enough information to say these two functions are dependent. All right. Then, furthermore, yeah, so based on this result, we just, try to extend a little more. If W equals 0 at one point, then, yeah, because here, we just extend it a little more in this way. 1 point is enough. W equals 0 at one point is enough to make y1, y2 linearly dependent. But y1, y2 linearly dependent would make this W expression equal to 0 on the whole interval I. So 1 point force W to be 0. 1 point force W equal to 0 on the whole I. See? 1 point can force the W to be 0 on the whole interval I. Why? Because coming from linearly dependent. Yeah, so this something special, something special. But here I want to emphasize, yeah, because this property looks quite special. Yeah. Why 1.0 can force the whole W function to be 0 on the whole interval? That's special, right? Yeah, because under normal situation, it won't be true. Under normal situation, it won't be true. Why it is true here? Because the reason it is true, because the y1, y2, they are two solutions of that system. That's important. We need to use that condition. y1, y2, they are both the solutions of this homogeneous linear second order ODE system. Yeah. Now, I give you another case. Yeah. If y1, y2, if we do not say y1, y2, there are two solutions of second order linear homogeneous ODE, PQ, that equation, just arbitrary two functions, then you won't have that. Okay? I can easily find two linearly independent functions. Yeah, two linearly independent functions. They can be 0 at one point, but on the whole interval they are not 0. Why? Because they are not a solution of that y double prime plus py prime plus q equal to 0. They are not a solution. So the solution condition is important. Yeah. Here, the reason you have this, because two solutions. Okay? All right. Yeah. So here, yeah. If there is xy at which not 0, only one point not 0, then you can say y1, y2, they are linearly independent. Yeah. Okay? Yeah. Yeah. So here, I emphasize, the exact meaning of this theorem. Yeah. Because remember, we will have our quiz number 2 soon, right? Yeah. Quiz number 2 soon. Yeah. Yeah. Because we close to finish our module 2. Yeah. We have part E. Yeah. Actually, after part E, I want to talk about PDE. So we have part F. I want to add one more part F. Yeah. But I plan to give you quiz number 2 this weekend. Yeah. So, because you just submit homework assignment number 1. Now, so this weekend you need to have some work to do, right? Yeah. Yeah. So that's quiz number 2. Quiz number 2, it does not cover all part module 2, yeah, because we Thursday we will do part E, yeah, part F next week. So it won't cover part F, yeah, only cover part A, B, C, D, E, yeah, quiz number 2. Yeah. Yeah. All right, yeah, that's it. Yeah.